Question number 1. A skydiver in the spread eagle position opens a parachute. Is the diver accelerated?
Yes.
The answer is yes. There is an applied force. If there is an applied force, there must be an acceleration. Which direction is it? Well, the force is up, so the acceleration must also be up. Now, I had a discussion with a couple people yesterday about this. Does this mean that the skydiver actually goes up? No. It means what? We're slowing down, right? As you're falling, the acceleration is this way.
So it's still
It means
going
you can slow
down.
down. Still going down, just slowing down, right? But still falling.
That doesn't make sense.
Still falling,
Yeah,
but slowing down.
so he's still going down.
Yeah.
Why did you say up?
The acceleration is up. I didn't say he goes up. None of these say that the direction that he goes is up, right? Acceleration and displacement are certainly two different ideas. A weightlifter lifts a 150 kilogram barbell from the ground. How does the force exerted by the lifter compare with the weight of the barbell? What does Newton say? Equal and opposite. The forces are equal. How then, Mr. Bennett, can he lift it? Well, at the start, is the upward force greater than the weight force? Yes, because you have to accelerate it. But once you get it moving, you only need enough force to balance the weight force, to overcome friction, kind of thing, right? So yes, you need a little bit extra at the start to accelerate it from 0 to speed. Once you get it up to a certain speed, you're just lifting the weight. So they are balanced. They are equal, the same. How does the force exerted by a lifter on the barbell compare with the force exerted by the barbell on the lifter? Equal and opposite. Equal. Equal. Listen, you guys. Here's the part where you listen to my wisdom. Suppose you put a wooden block against the wall and push horizontally to keep it from falling. Draw a diagram showing the forces on the block and cause of those forces. Pay special attention to the normal force and the weight force. Blah, 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 blah. In other words, draw a free body diagram. I'm going to make this even bigger. Well, let's start with our old friend gravity. Down, right? And normally, pun intended, the normal force is opposite to that. But normally, blocks slide down walls like that, right? They're normally sitting on tables. So the normal force is not that direction. In fact, the normal force is that direction, is it not? Right? Because the normal force is perpendicular to the surface. Is this hand applying a force? Yes. Which would in fact be equal and opposite to the normal force. But what the heck is holding it up? No, friction. Friction is what's holding it up. And as you push harder, do you increase the amount of friction? You do. Right? If you just very lightly held it on there, it would slide down. Does that make sense to you now? Yeah? That one's not an easy one. There's no doubt about that. Explain why an aluminum ball and a steel ball of similar size and shape drop from the same height reach the ground at the same time. Don't go looking for hard stuff. Because Galileo said so. Good answer. The acceleration is minus 9.8, and that's what it is. And yeah, you can discuss a little bit about, well, one's a little heavier, it's going to plow your air. Would the steel one reach the ground maybe momentarily? Maybe. Depending on how high up, right? Like if you drop from an inch off the ground, right? A foot, Top of Jake Brampton silo, maybe.
Off the high rise down.
Yeah. Would the high rise and Jake Brampton silo be a
Yeah,
bit?
Jake Brampton silo is just
Yeah? I don't know. The seniors block, just sort of kitty corner there from Mackenzie? No. But it's called the high rise. I'm not jumping off it. Don't drop cats off it. Yeah? Give some examples of falling objects for which air resistance cannot be ignored. Paper, coffee filters, feathers, Anything that's light and relatively large. Skinny cats. Let's do number 6 because it's sort of a package deal, right? I know I didn't say you had to do it, but give some examples of falling objects for which air resistance can be ignored.
Steel acme animals.
Okay? I'm thinking things like arrows, bullets, maybe shot puts, things that are relatively heavy and relatively small. What about golf balls? Jake, what's your experience with golf balls in the wind? Yeah, the wind actually moves them, right? Yeah, so yeah, not golf balls.
Depending how heavy your golf is.
Yeah. Okay, so there's the first 6, I guess. I'm going to give you some time to work on those. Let's have a look at a couple more sample ones. I think what I'll do is I will do samples 3 and 4, and I'm going to leave the weight one for Monday. We're going to talk about weight on Monday, so because I want to give you a little bit of time to work there. I was?
Yeah. You're like, oh,
You're not going to like this. You're not going to like this.
How do you speak to Peter?
There's a couple reasons why you're not going to like this. But fortunately, I know answers, guy, and he's giving me the answer. It was you guys that asked about, it was you, Billy, right, that asked about 32 feet per second?
Yeah.
Yeah. So we have 2 ways that we can do this. Because this is true. Has anyone ever been to Canada's Wonderland? Just north of Toronto there? Yeah? It's a lot of fun. I remember taking the kids there when they were younger. I was younger too, I guess. So that was the place, I will admit, that was the place where I actually was doing physics calculations in my head because I wanted to know how fast things were going. And I looked it up when I got home. There was this ride. I'll tell you the story about the ride. It's basically a giant swing, right? And it's these 2 poles like this, and they've got guy wires on them, right? And then they've got these other wires like this, right? And then they strap you in right here in a harness, right? And then there's like another pole in behind here, and then they basically pull you way back like this, way up in the air, kind of like a swing, right? Like a dad would sort of pull the kid up like this, right? Way up in the air, right? And then you're horizontal like this, and you pull the cord, and it lets you go, and you come screaming down on your belly, kind of flying like this, right? Well, there's all these people standing around. I'm watching this, and this girl comes flying down, and she goes right over top of me, and I realize, you know what? This is probably the worst place to stand to watch this, right underneath them. Like, you know, if the strap breaks, or bodily functions, malfunction, or she vomits, or... So I got thinking, I wonder how fast she's going, so I did some calculations. I think it was about 90 kilometers an hour. And they had a roller coaster, where you get into the roller coaster, like, you know how you normally, they sit you down, right? So they sit you in like this, and then they rotate you. So you're flying through the roller coaster. That's pretty cool.
They actually, in that roller coaster, if you wear glasses on it,
Yeah?
they tell you to take your glasses off. And I was told like 3 or 4 times as we were starting up to take off my glasses.
Yeah.
They're not responsible for losing.
And did you?
I've worn them my entire life. I know when they're falling off my face.
Well, have you ever done it at 100 miles an hour, though? Okay, so we have 2 ways of solving this problem. Canada's Wonderland does indeed, I checked it out, they do have a drop ride. You know those ones that they pull you right to the top and they let you go, right? It is 230 feet tall. How fast are you going when you reach the bottom? So we can do this 2 ways. We can either deal with feet, and the acceleration of gravity due to feet is 32, right? Or we can convert the feet to meters off the start. You want to just do that? That's probably the way that most people choose. Okay, so go ahead and get out the Googler. 230 feet is what? Oh, how much? 69 meters, is that right? I have no idea, actually. Okay. I'll take your word for it. Do I have it here? I got 70.1.
That's a big difference.
Yeah, I got 65.
Okay, well, maybe it's not exactly 3.3. 70.1 meters. Let's just do it this way. Okay, so what do we know? You're not going to like this. The initial velocity is 0, right? What's the acceleration? Minus 9.8. What do we need to solve? Oh, we know one more thing. Oh, I guess that's our D, right? Right there. That's our D. How fast are we going? We're looking for VF, and how long does it take to reach the bottom? Okay, well,
Oh, wait, this is tonight. Oh, tonight.
this is in that problem packet I gave you. You will need to focus, you guys. This is not going to be an easy one. Don't just write it down and say, I got it, because you're not. You're going to have to think along with me here. Okay, well, where to begin? Let's try this. V bar is equal to D over T. I only know what? I only know the distance. V bar is equal to 70.1 over T. Okay, that didn't get me very far. How come? Because I got two unknowns there. Okay, well, what else do I know? I got A equals delta V over delta T. Is that getting me anywhere?
If you do the V bar,
I know the initial velocity is 0.
and then you know the final.
No, I don't know the final. Easy, Lane. Just relax. Granny speak, please. Proper language, Lane. Okay, well, let me move that one out of the way. What else do I know? Here's one thing. Let's try this. V bar equals VI plus VF over 2. What do I know in there?
That's what I thought, but you can't.
No, that doesn't get me anywhere either. Although I will say that because VI is equal to 0, I could say that, right? Right? Because the VI is equal to 0?
You still don't know if you have.
I still don't know. Although I see V bar here and I see V bar here. Are they the same?
Yeah.
So does that mean that 70.1 over T is equal to VF over 2? Because those are both the same, right? Like I can take this thing here and put it in there, can I not?
I'm so confused.
Okay, well let's see where this goes.
You still don't know?
But I still got two unknowns, right?
So that's just quick. This question.
Well, let's try something else over here. How about I go minus 9.8? What do I know about delta V? Delta V is that not VF minus VI? Is that not true? And isn't VI equal to 0? I might be on to something here.
We don't have the time.
Oh, once again, we don't have the time.
I guess you just put an X and say can't, please.
If I had my superhero suit, I'd go in the back and put it on and come back as answers guy, and I'd let you know. But seeing as I don't, I'll just stay in my own clothes and tell you, we're not going to give up, Wayne. I'm not going to let you. Do you remember in math class doing questions like, pardon me? No, because remember, D has the V bar in it, right? Like there's no formula that has A and D in it. Is there? Have you guys done these questions in math yet?
No.
Systems of equations?
I've seen it.
Never seen them? Come on, someone nod. No? No? Uh-oh, okay. Trouble brewing then. Okay, well. All right, well, allow me to dazzle you. Okay, so we've got a system of equations here. We got VF and T, and here I've got VF and T, right? Is this VF the same as that VF? Yes. Is that T the same as that T? Yes. So what I'm going to do here is I'm going to take this, and I'm going to write this as VF is equal to minus 9.8 T. Lane, you need to watch.
Can't you just go 70.1 divided by 9.8?
No? What's D divided by A? That's no formula.
D, how long?
D divided by A.
No.
Well, that's the 70.1 divided by 9.8. That's D divided by A, isn't it?
Oh, at 9.8.
No, you accelerate at 9.8. You're not. That's not your speed. You guys are thinking this kind of stuff. This is what you're thinking. This is what you want me to do. You want me to put 9.8 into there, 70.1 there, and write. This is what you're saying, right? This is not how fast you're falling, that's how fast you're speeding up.
Okay.
I'm still so confused. Show us the right way.
I am showing you. Okay. I'll prepare to be dazzled on a Friday morning.
We just want to
Control that, Brad.
It's not making us learn.
Nah. VF over T. All I did was rearrange this for VF equals minus 9.8 T. All I did was take the T up there, okay? Now, does this VF equal that VF?
Oh my God.
Yes, it does. So I'm going to take this blue minus 9.8 T.
So now we're mixing our formulas.
Yep.
Holy.
I'm going to put this over there. And I'm going to write it over 2 is equal to 70.1.
Oh my God.
And now what did I just do?
I have no idea.
And now I only have one variable. It's like I'm a math wizard.
And is this going to be on the test?
Just for you, Lane. Now I'm going to cross multiply.
I guess I should call this one.
9.8 T times T. I'm going to cross multiply. 9.8 T times T is 9.8 T squared. 2 times 70.1. So I'm going to have you guys have seen this in math.
I've never seen this in math. I don't know what kind of math you went into, but I don't know. There's all.
Yeah, oh, by the way, this is all a big lie. Oh, this is T squared here, isn't it?
And I got time to square root. Yeah, you took the.
Uh-oh.
Couldn't you just solve that first and then put the?
Yeah? I got one more problem.
Square that.
Can't take square root of a negative. But clearly, things fall, and this is a valid question.
It doesn't work.
Or plug
Is it not falling down? Is that D, that 230 feet, not how tall it is? So isn't the 70.1, isn't the displacement negative 70.1? Is it not? Which now gives you a T value of 3.8 seconds.
How did that 3.8?
When you get to system of equations in math, and you will, this is an application of system of equations.
I did that 3.8 again.
I took 140.2 divided by 9.8, then I took the square root of it. Right? Like 140 divided by 10 is about 14. Square root of 14 is about 3.8.
Oh, so you just added a negative onto that.
Yeah, well, because it's down, right? Yeah. Okay, your mind should be sufficiently blown. You will not see any of those problems from here on in.
Yes.
I wanted to give you a little sort of future glimpse of what's happening. I want to show you that systems of equations is applied to physics. And I want to show you, this is the stuff you're going to get yourself into in grade 12 a little bit too, right? In a year from now, right? Just giving you a little taste, right? No? Come on, Graham. It'll be fun. Maybe you'll get to meet answers, guys. All right. How about we just do this easy one then? Stuff, Graham. Stuff.
If you count ball, this is going on there.
Oh. Suppose a ball dropped from a tower 70 meters high. That sounds the same as the last one. How far will it have fallen after 1 second, 2 seconds, during the 4th second? During the 4th second. What does during the first you got 0, 1, 2, 3, 4. You know what? I'm going to change the. Just let's get rid of those.
So after the first second, it'll have fallen 9.8 meters.
Will it?
If it's not, then
Negative.
Okay, there's the first second.
yeah.
There's the second second. There's the third second, and there's the fourth second. So during the fourth second, I just want to know
3, 4.
this distance here, right? From t is equal to 3 to t is equal to 4. So how am I going to do this? I got to find out where it's at t is equal to 3 and where it's at t is equal to 4, right? Okay. So let's find out where it is after 3 seconds. A equals delta V over delta t. Again, I'm encouraging you. I'm also, you know, the other reason for me doing this question is for you to realize writing the formula is important. There's no way to solve that without writing the formula. You got to get into that. Do it. Minus 9.8. Delta V, 3 seconds. What's 3 times 9.8? Graham's going to do it for us. 27.4? You're going to what? Don't be texting.
He's going to text that.
Negative 29.4. That's the change in the velocity. In fact, that's also how fast it's going at that point, right? Because it started at 0. Now I'm going to find the average.
Why isn't it negative?
It should be up. Graham, you can't be distracted by your phone right now. You have to be able to go more than a half an hour without looking at your phone. You have to. Adults do that. They do, Graham. It's expected. Have you seen me get up? I don't even know where my phone is. 14.7 is the average. So where is it at? Lane? Lane. Pay attention, man.
I'm writing stuff down there.
That doesn't mean you're paying attention. I can easily write stuff down without paying attention.
I can.
It's gonna be on.
This could be.
Could be.
Yeah. Yeah.
I mean,
Yeah. Absolutely. This you should be able to do. That first one, I was just blowing your mind. Well, so it's fallen 44.1 meters. Now, I guess technically, this minus, right? That's where it is after how many seconds? 3 seconds.
3 seconds.
But I want to know how far it's fallen between 3 and 4. So how do I get to that step? I got to do this all over again for 4 seconds, right? Go ahead and do that. Do this exact same series of steps, but instead of 3, put in 4. Do it up here. Is it 38?
No, that's 39.2.
Did you get 78.4? Negative 78.4? So the question, how far did it fall during that second, is going to be 78.4, subtract 44.1. How far did it fall during that very last second?
34.
Yeah, I could probably do that in my head. 34.3 meters. That I would expect you to be able to do.
Okay.
I'll stop talking now.
Oh, I didn't do the last step.
You gotta do that, yeah. Okay, I'll stop talking. You have a problem pack in front of you. You got lots of opportunity to practice. Solution, QR code is there, answers are there. Seriously, you gotta spend some time working through stuff. Okay? Monday I will talk about weights, and I'll give you some more time, probably another problem pack.
Mr. Bennett.
We're gonna get into friction later in the week.
The ball couldn't have fallen 34.3 meters because the tower was only 7 meters tall.
Ah, excellent point, Wyatt.
Gavin West instead.
The tower is only, I was waiting for someone to notice it, tower is only 70 meters high. Could it have fallen 78.4?
It could have fallen 70.
Can only have gone 70, right? So yes, it would have landed before the 4th second even had arrived. Gotcha.
If you didn't write that on your test,
No, I wouldn't do that to you on a test.
okay, good.
So it would have landed.
It would have landed
We went like down and then.
before time is equal to 4 seconds, right? Little bit of a trick in there. Most classes don't even spot it. In fact, I forget about it most years. Okay, I'll give you some time to work. Please use this opportunity. Go and visit.